Well, I'm very happy at this to sing for my ticket attending this marvelous Congress by introducing my colleague Antony Hewish, my colleague from Cambridge. We are both not only in the Cavendish laboratory where he spent his whole career, but we are members of Churchill College, where we at one time shared the problem of teaching physics to the undergraduates. I see it's a long time ago, but I remember vividly one day over lunch in the college, Tony started to tell me about the remarkably regular signals from outer space that he and his research student Jocelyn Bell were receiving in his new radio telescope. And in the search for an explanation, which he was still going on with at that time, he was beginning to wonder whether they were being sent from some alien civilization, which he called little green men. Well, at that point, alarm bells started ringing in my head because a year or so earlier, one of the mathematicians in the college had had to give up teaching following a serious mental breakdown. And I really feared that the same thing might be about to happen to Tony. This was a rather selfish thought because the main thing I thought about was how am I going to manage teaching the physics in the college on my own? Well, it's now history that over the next few months, Tony and his college found the explanation in terms of rapidly spinning neutron stars, now called pulsars. I don't know if he makes any money from the watch that you can buy called the Pulsar. And these pulsars have provided a platform for all kinds of exotic physics, including condensed matter physics, particle physics, general relativity, and they've provided Tony with a lifetime of interesting employment and, as we'll shortly hear, lecture material. And the Cavendish was delighted to have hosted such a splendid addition to the manifestations of Chadwick's neutron, and he swiftly made him a professor, promoting him out of college teaching. And so my selfish prediction was in fact correct. I had to look for a new colleague to share that work with me. But on the question of Tony's sanity, I'm happy to admit that I was spectacularly wrong. That to receive messages from an alien intelligence in outer space would certainly be very exciting and could perhaps create mental and psychological stress for some future astronomer. The same kind of thing you can say of messages received from the intelligences in Stockholm that you've got a Nobel Prize. That can be pretty disrupting. And Tony, I think, is greatly admired by me as well as many of his colleagues for his success in maintaining his natural modesty and equilibrium in these situations. I'm very happy to introduce Antony Hewish.
Thank you, Archie, for those nice remarks. You have been a valued colleague of mine in Churchill College for many years. It's a great privilege for me to be here today and partaking in this magnificent celebration of Einstein's Annus Mirabilis. And I must thank most sincerely my colleague, Professor Pedro Echenique, for inviting me to participate in this event. It has been a really wonderful and stimulating occasion. In my talk, what I shall try to do as simply as I can is to explain how these amazing stars, called pulsars, actually work. What is the underlying physics? It's not all fully understood so far, but it involves a great deal of interesting physics. But I would also like to mention briefly, but only briefly because the following talk I'm sure will go into this in more detail, but mention briefly how pulsars are connected to Einstein. I think if pulsars had been discovered when Einstein was alive, he would have absolutely loved these stars, because pulsars provide two things of great importance in experimental testing, if you like, of Einstein's theory. First, they provide enormously powerful gravitational fields, as I shall explain, immensely strong gravitational fields. And secondly, they provide a means of measuring accurate time in an astronomical context. By accurate time, I mean pulsars provide clocks which are currently keeping time to about 1 part in 10 to the 15. That is to say, they are comparable to atomic clocks, and they will keep time to better than 1 second in about 30 million years. Now, those two features, strong gravity and accurate measurement of time, provide a kind of cosmic laboratory in which one can test out some of these ideas, these wonderful ideas Einstein had about space and time. And they test them in ways which, at the moment, one can see no other way of doing it. But first, I would like to show you a neutron star. What you're looking at is one of the most famous objects in astronomy. It's the remains of a star which has exploded. When stars run out of nuclear fuel, gravity must compress the material, and ultimately the material is pressed into a different form, as I shall explain in a minute, and the collapse takes place with great violence. An enormous flux of neutrinos is released, and the result is an explosion. And what you're seeing in that illustration is the result of a star which was seen to explode in the year 1054. Currently obtainable pictures, images like the one you see, are therefore images of the explosion around 950 years after the explosion happened. What you see there mostly is expanding gas, filaments moving outwards at many thousands of kilometers per second. And it is in the center of that nebula that you can find a pulsar which actually is visible. Most pulsars are not visible with optical techniques. Most pulsars require radio telescopes to see them. But in this case, this is one of the rare examples of a pulsar that you can actually see. Now, from the movement of those expanding clouds of gas, you can use velocity vectors, measure the direction in which the outflowing gas is moving with time-lapse photography, and you can project back that motion and calculate where the origin of that explosion should be. And that takes you back to a star towards the center of that nebula. The star there is, well, at the end of that arrow, I'm not quite sure how well you can see it, but at the end of that arrow, there is a pair of stars just resolved, and it is the star on the bottom right hand of that pair, which actually astronomers had thought was the remnant of that explosion. It was predicted in the early 1930s, soon after Chadwick discovered the neutron, that under sufficient compression it would be possible to have stars which were composed almost entirely of neutrons, and they would be most remarkable objects, because at the density of closely packed neutrons you can compress the mass of a whole star into a sphere only 10 kilometers or so in radius. And so a neutron star is a very remarkable object. And it was not until pulsars were discovered that it was realized that neutron stars were really detectable. Let me just show you some more pictures. If we now take an expanded view of that central region, it was in 1968, roughly 1 year after our discovery of pulsars at Cambridge, that close observations were made of the center of that nebula, because it was at the center of explosions of that sort that neutron stars would be found. And after we published our pulsar discovery, then it was realized that neutron stars, I had suggested that neutron stars were the possible cause of our pulsed radiation. I will come back to that in a moment. But we had thought that neutron stars might be responsible, and a radio-emitting pulsar was discovered at the center of that nebula. Closer observations showed that it was in fact emitting flashes of light in addition to flashes of radiation, which makes it a remarkable object. On the right, you see a whole series of stroboscopic photographs effectively taken at 1 millisecond intervals, which show that star on the bottom right-hand side of that pair coming on and off. What you see there is a whole sequence. It's in fact a double flash. On the first two columns, you see the star flashing fully for about several milliseconds duration. It flashes twice, and then there's a gap showing just a single star. The light-emitting star has simply vanished on the right-hand column there, and then the whole cycle repeats. This happens about 30 times a second, and it is one of the rapidly flashing pulsars. If you have a more detailed look at the radiation coming from that central star, here you see across the spectrum what those flashes look like. We start at the top. They're slightly displaced so that the overlapping peaks can be seen more clearly, but they are essentially simultaneous. And at the very top you see what those flashes look like at normal radio frequencies, VHF, as we say, the sort of frequencies used in broadcast. And as you come down, then you see towards the bottom, you see the optical flashes there, a double flash towards the bottom, and the spectrum extends to X-rays. This is also flashing at X-ray frequencies, and is one of the rare examples of these flashing pulsars which emit over the whole spectrum. As I explained earlier, normally pulsars only emit radio frequencies, so you need radio telescopes to see them. Well, now, that is a very remarkable sort of radiation from a star, and it's taken really quite a long time to understand how stars can produce radiation of that sort. But the simple model which emerged within 1 year of our discovery, a theory essentially due to the late Thomas Gold of Cornell. His idea was that if you have a neutron star which is producing a beam of radiation, in the example shown, the rotation axis of the neutron star is vertical, and it's producing a radio beam aligned along another axis, so that as the star rotates, then that beam will sweep around the sky. And if you're in the direction of the beam, just like a terrestrial lighthouse on a cliff, then you will see a flash every time the star rotates. So that this was the simple idea, the rotating neutron star lighthouse, that within 12 months of our discovery was the generally accepted explanation of how it is that a star can produce flashes of radiation of this kind. A very, very simple model. Well, direct evidence that you do have something spinning at the middle of that nebula came much later. Here you see much more recent observations of that Crab Nebula supernova explosion, which were taken with X-rays, and it's really impossible not to see that you're looking really at a vast rotating system there. That what you're seeing is much, much larger than the star itself. It occupies a large fraction of the supernova explosion, the supernova remnant that I showed you. But it's hard not to see there that there really is something rotating at high speed and throwing clouds of hot X-ray emitting gas into space, and running slightly slantwise through the very center. You can just about imagine a rotation axis. These images have not yet been fully and satisfactorily analyzed, but everybody, I think, agrees that this is a very fine illustration, really, that the rotating neutron star idea has to be correct. Now, in this case, we're dealing with a star which is spinning at speeds of about 30 revolutions per second. It's spinning fast because it's a neutron star that was formed only just over 900 years ago, as we see it in the sky. Most pulsars are much slower, with pulse rates of around 1 second or some fraction of a second, but this is a rather fast one because it's a very young pulsar, and most pulsars are quite old objects, over 10 million years of age. Here you have one which is only around 1,000 years of age, and therefore it's spinning quite fast. If you measure it carefully, you can see that the spin is actually slowing down. And if you do more careful physical measurements and determine the rate at which that slowdown is happening, you can see that if it were a spinning neutron star, then the loss of energy of that spinning system would really be just about sufficient to provide the energetic particles that cause that X radiation. X radiation from the Crab Nebula had been known for a long time, ever since the early 1950s. The X radiation was a little bit later than that, 60s, but the problem of the light and X-rays from the Crab Nebula had been a classical astronomical problem, because the energy loss would indicate that the nebula, without an internal source of energy, would actually dim in a time substantially less than 900 years. In something like a century, the radiation should fade, but it doesn't, it stays there. And that mystery was solved when the neutron star, when the pulsar was discovered, because here was a source of energy. And from the mass of the expected mass of a neutron star, which is roughly the mass of the sun, somewhat heavier, then that object spinning and slowing down would produce exactly the energy needed to power the nebula, and that was a success which really encouraged astronomers a great deal. So although this spinning idea may seem a little strange, nevertheless there's strong evidence to support it, and since then there's been increasing evidence that we really are dealing with rotating neutron stars. The actual discovery in 1967, I'll just say a word or two about that, was one of those lucky accidents that sometimes happen in science. Well, I shouldn't call it accidents, I should say lucky occasions. It's like the discovery of X-rays, or the discovery of penicillin, or the discovery of the microwave background radiation. These groundbreaking discoveries were not sought. They simply came by chance to observers who were working in the right field at the right time. And the history of science is really, there are quite a lot of occasions like this when a new discovery, as it were, changes the course of a subject, and it comes not by a carefully planned experimental search, but nature actually presents the results to you, and when this happens, of course, one is incredibly fortunate. If you go back to the 1960s, radio astronomy was in its early stages. Instruments then were not able to image the radio galaxies that were being discovered. It needs high angular resolving power, very large radio telescopes to make sharp images so that you can really see a picture of a radio galaxy. And that was very difficult. We had no means of doing that in the 1960s when research was, well, in radio astronomy was just beginning. But one thing we did know, there was an interesting type of radio galaxy called a quasar. This was observed to be a highly compact sort of galaxy, sometimes so compact that it looked like a stellar object. And for some years, it was not at all clear what they were, because galaxies normally, as you know, are diffuse extended features, and that applies to radio galaxies, radio-emitting galaxies, as well as the more familiar optical galaxies, which you've seen pictures of already in this session. But the quasars were distinguished because they have extremely bright, small areas of extremely bright emission. They have extremely hot spots, which are normally near the center of the galaxy. And we had discovered previously at Cambridge, I and others, that quasars had often a fluctuating intensity. The intensity was not steady, as is normally the case for a galaxy. It was fluctuating on a time scale of seconds, and we understood and explained this twinkling effect of quasars in terms of distortions of the incoming radio waves through the solar wind. The sun is always emitting ionized gas into space. This is called the solar wind. It blows out through the planetary system at speeds of typically a few hundred kilometers per second. And the gas, because it's hot, is ionized, and radio waves penetrating, coming through this gas on the way to the Earth, are phase modulated by density irregularities in the expanding gas. And it was this that causes quasars to twinkle. The intensity fluctuates in just the same way as a twinkling star is seen to twinkle as you look at it with your eyes. So, but normal radio galaxies, being larger, did not show this effect in just the same way that the moon and the planets are not seen to twinkle in the sky. It's only the tiny, small, angular-sized stars that do this. But the quasar twinkling, I thought, would be a very good way of deciding which of our several hundred galaxies that were then known had this quasar property. Without being able to image it, at least we knew that it had a very bright, hot region within the radio galaxy. So I designed a somewhat unusual radio telescope to make a sky survey of all the objects in the sky, and that would show which of our galaxies showed this twinkling phenomenon. Now, because I wanted to look at a large number of radio galaxies, the telescope had to be rather large. I needed a radio telescope having an area of about 2 hectares. Such an instrument didn't exist, and even today there are not many telescopes of that area in existence. But because really of simplicity, I decided that the most convenient way of constructing an instrument like this would simply be to spread over a field an enormous number of receiving elements, rather like just ordinary radio antennas. I was operating here at a wavelength of around 3.7 meters. You have to use a long radio wavelength, a fairly low radio frequency, because the twinkling phenomenon in the solar wind is a physical plasma effect, which shows up most strongly at fairly low radio frequencies. You could not use it at the frequency centimeter wavelengths, the sort of frequencies that were normally in use for radio astronomy. So I constructed this rather strange-looking instrument. You can only see a small part of it, but it is essentially about 2 hectares of area completely filled with about 2,000 receiving antennas. And in order to use this phenomenon to measure quantitatively angular sizes, which I wanted to do, not just to know which of these galaxies were twinkling, but to be more quantitative and make a measurement of the angular size of the quasar source, it was necessary to make observations over the course of the year, so that the angle at which you observed the source, the solar elongation as we called it, was variable, and as the line of sight approached the sun at its nearest point, you would get more and more scintillation, and from the way that curve developed, you could measure quantitatively the size. So we constructed this antenna, and in 1967 began a sky survey in which the whole point of the survey was to see, of all the sources in the sky, which ones showed the twinkling effect. Well, this was on the top there. You see one of the standard recordings that we were making during the survey, and these, I should remind you, were the old days. Computers were only in their infancy, and the idea of digital recording systems was not. It was a very expensive and awkward thing to do. It was much better to record your signals then, just with a pen on a moving paper chart, and on the top there you see the standard sort of signal that the survey produced, and you can see in the arrow in the middle there, called CP 1919, what seems to be a rather weak scintillation lasting for a few minutes. That recording was made on the 6th of August 1967, and the strange thing about it, which was spotted by my student Jocelyn, was that this twinkling source was observed in the middle of the night. Our observations were continuous over the 24 hours, day by day, so that we were observing all the time. And mostly this twinkling phenomenon, the scintillation, was only strong when the line of sight passed reasonably close to the sun. In other words, was a daytime measurement. Here, the strong scintillation, it corresponds to 100% fluctuation of intensity when the source was nearly at midnight as we observed it. So that was very odd, and I thought that it might be radio interference to begin with. A little bit further along on that record, you do see on that second arrow on the right some interfering signal, which is simply a motor car driving past the telescope near Cambridge, and that's the sort of thing radio astronomy is bothered with all the time. Radio emission, just radio noise from a car or a motorbike or something like that. And I didn't take this to be real until we'd seen it several times. But when we'd seen it several times, I decided we had to do some investigation here. And I asked Jocelyn to install another pen recorder that we had, and that's shown on the bottom track there. You can just see it, I think. A much faster chart speed, and to make special observations of that particular fluctuating signal to see what was going on. It might have been an object like a flare star, for example. The sun emits radio waves, and I was just thinking it might be something like that, but more distant. Well, it turned out, to our amazement, that there were flashes being emitted quite regularly, as you see along the bottom track. Flashes there at intervals of just about 1.3 seconds. And it was around about this time, that recording there you see is November 28th, 1967, when I began to breathe words about this to my colleagues in college. And it was, in fact, a very senior geophysicist to whom I mentioned this result. And he said, well, if you're getting signals like this from a great distance, and the signals are wideband signals, then the most likely explanation is an alien signal of some kind. He was quite serious about it. I have to say I hadn't taken it too seriously myself, but I couldn't ignore the idea that these really were signals coming from outer space. It was not long before I'd got some estimate of the distance, which turned out to be about 100 light years, and from the very width of those pulses you can see that you must be dealing with something which is smaller than a planet, so that, or at least not larger than a small planet, and adding up all those things really points in the direction that you are receiving an intelligent signal of some kind. It just simply does not look like the natural signal you get from any ordinary star or galaxy. But there was a test I could do which really eased my mind. After a few days of accurate timing, you can see on the bottom record again second pips on that time chart there at intervals of 1 second, and I realized that it was keeping time to better than a millionth of a second per day, and that gave the possibility that if the signals really were coming from an inhabited planet, that you could detect the orbital motion of the planet using the physical Doppler effect. If the object sending the signals was in orbit, then at times the orbit would be accelerating the object. The so-called planet would be moving towards you, or at other times of the year it would be moving away. This would cause an observable Doppler effect, and you could measure the orbital motion. After 3 weeks measurement, which took me into the new year of 1968, then I'd failed to failed to detect any orbital motion, and I have to say that I was greatly relieved, because if you do start receiving signals from outer space, it becomes a little more than ordinary science. It becomes somewhat political, you might say. The late Sir Martin Ryle, who was head of this research group at the Cavendish, said, well, if it is intelligence, we must not try to respond in any way, send a signal back, because if you do that, perhaps this is exactly what the signals are for. They're trying to locate a green, relatively uninhabited planet in order to occupy it and find somewhere to live, because they were overcrowded on their own planet. He felt it might be a dangerous thing to do. Well, I must confess I wasn't really thinking in that direction myself, but it was a great relief when the planetary origin, the intelligence origin, went away. And as a radio astronomer, I didn't know a great deal about stellar astronomy. I wondered what sort of stars could be as small as a planet, and the only two possibilities were white dwarf stars and things then which were highly hypothetical, called neutron stars. It was predicted in the 1930s, as I mentioned earlier, that neutron stars could exist, and soon after the discovery of the particle, and a neutron star would be just contain the mass of the sun in a sphere only a few kilometers, 10 or 20 kilometers in diameter. So we published the results, and I suggested that it was most likely a neutron star, but we could not rule out at that stage the white dwarf possibility. Well, later work confirmed the neutron star hypothesis. If you're going to understand neutron stars, you need just a little physics. How is it that you can get a star made more or less entirely of neutrons? And I'd just like to do some very elementary physics here. On the top, I've got schematically an illustration of what normal solid matter, the kind of matter our world is made of, what it looks like. It's composed of close-packed atoms in which you have the nucleus at the center and orbiting electrons. I've shown those schematically as blue circles. The nucleus is surrounded by orbiting electrons, and what gives matter its density is when you push atoms together until those orbiting electrons, the orbits begin to overlap. Then you get repulsion between the individual atoms, and that leads to crystal structure and so on. But what you see there is just schematically how it works. Now, electrons are particles, and of course the particle-wave duality applies to them. Indeed, the whole structure of atoms depends upon the wave properties of the electron. And very roughly speaking, the wavelength of those electron particles in an atom are the size of the atom. I've shown the electron wavelength effectively on the right up there, a wavy line, and the electron wavelength, particle wavelength, is about the same size as the orbit. That is how the orbits are formed. Well, what happens then if you're going to crush and squeeze ordinary matter? You can't do these experiments in a physics lab. You can't crush material to the extent that I shall need to explain a neutron star, but we can imagine schematically what will happen if we start compressing matter. And that's shown in the next box down below, called degenerate matter. As you squeeze the material, the electrons, being Fermi particles, fermions, you have to have the electrons cannot pile into the lowest state of energy. They all have to have their individual energy states. And without going into detail here, as you compress material containing electrons, the electron wavelength has to fit into a smaller and smaller volume. As you see in the middle there, the electron wavelength has to become shorter as you squeeze material, simply to fit into the available volume. And according to the famous particle wavelength equation, the energy of the particle is inversely proportional to the square of the wavelength, so that as the particle wavelength decreases, so the energy of the particle increases. So the result of squashing material is to increase the energy of the electrons, and if you squeeze material enough, you can give the electrons enough energy to no longer be attached in orbit about individual nuclei, but the electrons fly freely through the material, just like conduction electrons in a metal, and you get what we call degenerate matter. When you squash matter down until it has about a density of 1 ton per cubic centimeter, then all the electrons are moving freely through the material. The residual nuclei form a regular lattice, and this is what's called degenerate matter. And this is, you find degenerate matter like that with a density of about 1 ton per cubic centimeter in stars, in white dwarf stars, which are stars which have run short of fuel and simply been compressed by gravity to the size of a planet, about the size of the Earth. That is what a white dwarf star is. It's simply the compressed ashes of a star that has used up its nuclear fuel. Many white dwarf stars are in existence and detectable. But what happens when you squeeze matter even further? This is the possibility that was foreseen in the 1930s. Well, what happens then is that as you go on squeezing, the electron energy continues to rise, and ultimately you get a reaction between the protons and the electrons, which is shown on the bottom right. Protons and electrons combine to form neutrons. This is exactly the reverse of what happens at normal densities of materials in a physics lab. If you create a neutron in some kind of reactor or nuclear reaction, then free neutrons decay into electrons and protons in a matter of minutes. But under high enough pressure, because the electron energy becomes so high at very high density, it is preferable, it's energetically more favorable for electrons and protons to combine, so that the electron no longer, as it were, needs that high energy as a free particle. So the reaction goes backwards, and you get the creation with neutrinos included, as I've shown on the bottom there. The reaction goes in the reverse direction, so that electrons and protons combine to form neutrons. The radioactive decay, as it were, works backwards. Well, now, if you squash neutrons together, then you get a very strange material, neutron matter, which contains something like 1 billion tons per cubic centimeter. At that density, the mass of a star will fit, as I've said already, into a sphere of diameter about 20 kilometers. It's hard to imagine a material in which the density is as high as 1 billion tons per cubic centimeter, but it might help to imagine that you have a coffee spoonful of this material, and that coffee spoon of material would be enough particle material to make about 1,000 large ocean-going liners. I mean, it really is an amazingly high density of material. It's extremely hard to imagine, but that's what the physical property of a neutron star would actually be. Now, what would a neutron star actually be like? Of course, it isn't just a ball of neutrons, because there's a pressure gradient as you go from the outside to the inside, and very schematically, a neutron star is expected to look something like I show you here. You have a rigid crust on the outside of the neutron star, which is degenerate matter, the kind of material white dwarf stars are made of, and as you go down, the pressure rises, you get more and more neutrons, and ultimately the bulk of the material is in the neutron form. There are traces, of course, of electrons and protons as well, but as an approximation, this is the sort of physical body that you'd end up with. Well, as you go down nearer to the center, problems arise. We don't know enough about particle interactions to say what might be going on at still higher pressures at the center, and it's not inconceivable that you would have a core made of quarks. But that's simply speculation. Not enough is known to work out a detailed model there. One of the strange facts is that although that green material which illustrates the neutrons is at enormously high density and also relatively high temperature, because when stars collapse it's a very energetic process, and the residual neutron star would have a temperature of something like 10 or 100 million degrees Kelvin, a very high temperature as a result of the explosion. Of course it cools, but you would expect neutron stars typically to have temperatures of around 1 million degrees Kelvin. Nevertheless, the particles are so closely packed that their wave functions overlap. And what happens here is that the neutrons pair up. Neutrons, individual neutrons, are Fermi particles, they're fermions, but if you pack them closely enough, they will form pairs, Cooper pairs, just like superconducting electrons. And the result is that this neutron material is actually an extremely dense quantum liquid. It's an enormous volume of Bose-Einstein condensate, and that is what the interior of a neutron star should be. Well, this is not just wild theory. This can in fact be checked to some extent by observational methods. But first of all, let's think a little bit more about this immense gravitation. I said that neutron stars provide enormously powerful gravitational fields. Well, one of the effects of gravity is that clocks run more slowly in a gravitational field, and at the surface of a neutron star, then clocks would lose about 2 hours per day. If you put a light ballerina on the neutron star, she's going to weigh many millions of tons. That's actually an underestimate that's put there. The calculation wasn't quite right. But of course, if you visited a cold neutron star and tried to stand on it, you wouldn't be very satisfactory, because you'd be immediately squashed into a very thin layer on the star. And ordinary material simply cannot exist on a neutron star. So gravitation is enormously powerful around a neutron star. This is going to be why neutron stars are in fact useful in checking gravitation, Einstein's theory of gravitation. But come back for the moment to this question of the liquid interior. How do we know it's a quantum liquid, not just solid neutrons? Well, every now and again, close observations of some pulsars, particularly the younger ones, show that the fluctuating signal, the pulses, the rate of the pulses, suddenly increases by a very small amount, by about 1 part in a million. Well, that would be actually a large jump, but sometimes the pulse rate can jump, let's say, by about 1 part in a million or less. This is not frequent. This happens once every several years in certain cases. But if you plot what happens to the pulse rate, well, it's slowly decreasing because of the normal loss of energy of the neutron star. But when you get one of these so-called glitches, the period suddenly jumps, and then it begins to recover its old value. It never quite gets back to its former value, but it recovers with a kind of exponential recovery rate. Now, solid-state physicists will say that if you have a kind of an earthquake, a starquake on the neutron star, which changes its shape, you might have been asking in your mind, how can an isolated star change its spin rate? Well, it is because it's a complicated structure and it can change its moment of inertia. just like a skater can suddenly spin faster by reducing dimension about the spin axis, pulling in the arms or something like that. So a neutron star can spin somewhat faster by rearranging the material within it. And one of the ideas is that the rigid crust and the quantum liquid, the superfluid interior, can interact in just this kind of way. Let's imagine, this isn't the detailed model, but imagine that the crust, that rigid crust of the neutron star, in slowing down, it tries to become more spherical, but let's suppose that because it's so rigid, it kind of cracks and becomes suddenly slightly less oblate. Well, the outside then must spin a little faster, because that is what controls the lighthouse beam, and that is what we observe. So we're observing the spinning of the outer crust. But the inside of the neutron star is coupled to the exterior shell, and the coupling can be rather weak if it's a quantum liquid, so that it doesn't immediately spread the change of angular momentum around the star. The recovery is slow. That represents momentum, transfer of momentum from the faster outside to the more slowly rotating inside. And this phenomenon now has been studied over many years, and it's become quite clear that the effects, to explain them, you must have a Bose-Einstein liquid within a neutron star. Without that, the coupling between the exterior and the interior would be virtually instantaneous. And instead of taking weeks to recover the original period, it would be a fraction of a second, and you cannot explain the sort of phenomenon that I've shown schematically there on that slide. So there's very good observational, actually, very good observational evidence that neutron stars really obtain quantum liquids. Now, just a brief word or two about Einstein. You've heard a lot about Einstein already, but I make no apology for just mentioning it in passing here. This is going to be dealt with by the following speaker, Clifford Will, but I'd already got these illustrations there, so I might as well explain to them. And I think the ideas of relativity, although some of them are rather difficult, some of them are also rather easy, and for those who might be fresh to really trying to understand what Einstein's relativity theory is all about, then it's good to have something to hang on to. And this is where I usually start teaching my students in Cambridge, if I'm teaching them simple relativity physics. And you can immediately see that the experimental fact that the speed of light is an absolute constant, independent of how the radiation is emitted, the movement of the radiator or the movement of the observer, it makes no difference. The speed of light is an absolute constant, however you measure it and whoever observes it. Now, a simple way to see that time really then cannot be universal, is to see how a pair of events would look to two different people. Supposing you have a stationary box on the top there, and you have a light source at the center which sends a light flash, a pulse, in both directions. Well, clearly the box is a symmetrical situation. The light pulse reaches each end of the box at exactly the same time. But now move that box very rapidly to the right, and imagine what happens then. Well, the speed of light is the same to you standing outside the box, and it's quite clear that the light travelling to the left is going to hit the wall much sooner than the light travelling to the right, which has much further to go, because the light is catching up the moving box, as it were. So it's quite clear that if you're standing outside that box, the light flash will not reach each end simultaneously. So that events that are simultaneous if you're standing inside the box are not simultaneous if you're standing outside and watching the box move past you. So this is the kind of thing which one can see qualitatively, and even the mathematics is not very tricky. that in that case, light behaves, the occurrence of time must be different for different people, and an event simultaneous to one person will not be simultaneous to another. Another effect which is easy to understand, simply qualitatively, is this business of light running more, the rate of a clock being slowed down when it moves. Time runs more slowly for something in motion. Take a light flash clock, as I've illustrated on the top there. Supposing your clock is at the bottom and it has a flashing light mounted on it, and 1 second, it's a rather large clock, but 1 second is the time it takes the light pulse to be reflected from a mirror at the top and then to come back down to the light source again. Supposing that represents tick-tock as the light pulse goes up and down. All right, there's your light flash clock. But now put that clock make it move past you on a moving box or in a train. It's clear now that the light pulse has much further to go, because as you see it, the light is traveling at just the same speed, but the mirror is moving sideways, and the box has moved towards the right considerably before the light flash comes back. And so instead of going tick-tock, tick-tock, it goes tick-tock. And the moving clock, therefore, runs much more slowly. And these effects are very easy to see qualitatively. Well, they're part of engineering practice now, unless you make allowance for effects like this, the effect of gravity on clocks, the effect of moving clocks. As has already been said, apparatus that requires accurate time, such as the global positioning system, the GPS navigation system, unless these effects are built into it, the system simply would not work. In the case of the GPS, you have to allow for the gravitational effect, and also the effect that the satellites launching the signals are in motion, are in orbit about the Earth, and without that it wouldn't happen. These effects, in general, are not large. If you spent your life aboard an aircraft traveling at the speed of a normal jet today, if you were an air crew and you spend all your life doing that, then you will gain perhaps something like a thousandth of a second over your whole lifetime. That's not very much. But you can make objects move fast enough that you could increase a human lifespan to something like 2,000 years if you could make spacecraft that can travel as fast as the particles we use in laboratory experiments. And indeed, the decay of particles at high speeds has been shown to show precisely this slowing down effect, and the increase in the lifetime is just an observable fact. Now, another little bit of relativity, and this is where I shall come back to pulsars in a minute, is this question of what happens to relativity when you have two objects in orbit about each other. Well, they will emit gravitational waves, that is to say, crudely speaking, ripples in space-time. The system will lose energy because it is propagating gravity waves. And that is one of the things I'm going to come back to in a minute, because this is relevant to pulsars. So orbiting bodies will tend to lose energy because they are gravitating, they are radiating gravitational waves, curves in space-time which propagate at the speed of light, very similar to electromagnetic radiation. I'll say a little bit more about that later. Another effect which is entirely due to Einstein and is not Newtonian is this question of orbital precession. On the bottom left there you see very schematically the effect of the planet Mercury in orbiting the Sun. The planet Mercury has a slightly elliptical orbit. It's a great exaggeration what I've shown, but the orbit, instead of being an absolutely static ellipse, the orbit tends to precess around. It rotates steadily to the left, as I've drawn it there, and that precession was known to astronomers in Einstein's time, and was one of the effects which is theory of general relativity explained very well, but that orbital precession there is another non-Newtonian effect which is relevant to pulsars, as I shall come to in a minute. And a final one is that if you take, as in the bottom right, two bodies in orbit about each other, and one of them is spinning, the one on the right, as I've sketched it there, then the spin axis of that will precess. And this is what is called geodetic precession, and this is again an effect which is entirely non-Newtonian and entirely due to Einstein. Just as a digression, what actually is the effect of a gravitational wave? It's one thing to say that it's a ripple in space-time, it's a propagating gravitational field. What would it do to you? Well, if you just taking all of that illustration for the moment, the way I've said that gravitational waves come when you rotate particles or masses about each other. You're well aware of your cell phone and the little antenna sitting on it, and its vibrating antennas, they're vibrating electrons in that little antenna that launch radio waves. Now, in a very similar kind of way, if you spin a dumbbell, as I've shown lower down, then that dumbbell is going to launch gravitational radiation in a similar way to the electrons launching radio waves in your cell phone, and those waves are going to travel out into space at the speed of light. And what would they actually be like? Well, in a ridiculous situation where you make the strength of the gravitational wave enormous, then that ripple in space-time passing you will have the effect, first of all, of stretching you if you're in a certain place, as I've shown in the middle there. You take our hunter there, his normal size on the left. The gravity waves comes past, and first of all he will be stretched, and then he will be compressed and also extended sideways. It's a propagating force which has the character that I've illustrated, and that's what a gravitational wave actually does. That's what space curvature actually means for physical objects. Well, I'm sure you'll hear much more about that. Well, now, in around 1973, two radio astronomers working at Princeton, namely Joe Taylor and Russell Hulse, were using this radio telescope, a large radio telescope in Arecibo, on Puerto Rico, and it is an extremely large reflector there, about 1,000 feet in diameter. Radio waves falling into it are reflected up to the focus at the top there, and it's a very sensitive radio telescope that has been much used for radio astronomy. And in 1972, Hulse and Taylor discovered a pulsar which was obviously in orbit about another neutron star. From the careful timing of the pulses, it was quite clear that a single rotating isolated neutron star would not be satisfactory. It was in orbit about something, and a very unusual object. It was in orbit about an invisible companion, which also had to be a neutron star. I won't go into all the arguments there, but it was clear that this had to be the case. Now, the whole thing is extremely compact. In this case, the orbit would more or less fit into a sphere about the size of the Sun. So you have two neutron stars extremely close to each other, in orbit about each other, with a period of about 7 3/4 hours. That was the orbital period of these binary neutron stars. And relativistic effects are therefore possible. The so-called geodetic precession of the pulsar on the right, it has a precession period there of about 300 years. This has already been detected. The lighthouse beam is changing its beam shape, which can only happen if the rotation axis of the neutron star is changing. And it's happening so fast that it won't be too long, perhaps 30 years, before that pulsar has disappeared from view, because the lighthouse beam is no longer pointing in the right direction. So we now know that geodetic precession, as predicted by Einstein, entirely non-Newtonian, that is in fact happening. That has been observed. But more importantly, the orbit here, the overall binary orbit is shrinking. And Joe Taylor at Princeton and his colleagues have been measuring the shrinking of that orbit as it loses energy over many years. You see observations there over 25 years and more. The graph shows how the orbit is essentially shrinking. It's a timing measurement, so the actual axis is a time axis there, but don't worry about that. What you're seeing there is the effect of the shrinking of the orbit. The orbit of the binary is shrinking by about 1 centimeter per day, so that over the year it will shrink by about 1 meter. Well, you can calculate from the known masses. I'm not going to explain how the masses can be determined, but from that orbit, as with other binary stars, which aren't neutron stars, you can determine the masses of the stars from the orbital characteristics. And in the case of the binary pulsar, we know that the masses of those neutron stars is about 1.5 times the mass of the Sun. From the rate at which the orbit is collapsing, it is possible to deduce that gravitational waves are being released. And knowing the masses of the system, the prediction can be made of how fast that orbit should be collapsing, and the smooth curve that you see there is the prediction made using Einstein's theory of general relativity. You see that the points lie on the curve with exceptional precision, and I should stress that the curve is the prediction of Einstein. It's not the best fit of the observers to the points. It is the prediction of Einstein's theory, and the observations fit that very precisely, which confirms the gravitational wave theory to an accuracy of much better than 1%. So you see that there's a very close connection here between Einstein and pulsars. Well, just to conclude, pulsars are providing accurate clocks of enormous value to us, and what sort of pulsars actually does one use to do this work best? Well, here is a picture of the so-called fastest pulsar. It is a pulse rate of about 1.5 milliseconds. That's to say the star is rotating at around 600 revolutions per second. And in this case, you can see a pulse from each part of the radio beam. It's as it were the north and the south pole. It's a misaligned axis, magnetic axis, along which the radiation is emitted, and that shows you the sort of pulsar which is useful in this context. That is so far the most rapid pulsar that we have. And these highly spinning pulsars that are the most accurate clocks are not just the result of a single stellar explosion, they're the result of something a little more complicated. Many stars in astronomy are binary pairs. They exist as a binary combination. It's a very common arrangement for stars to be in our galaxy. And of course, the stars evolve separately, and one star can become a supernova and lead to a neutron star at the center, while the other star is still there. And in this case, you have a red giant star next to a neutron star which is formed, and the gravitation of the neutron star is such that it can suck material from the large white dwarf. And that material flows down onto the neutron star and makes it spin much faster in order to conserve angular momentum in the whole system. You can't lose angular momentum, and you're really transferring angular momentum from one star to another. This causes the originally formed neutron star to spin that much faster, and this is how you get neutron stars spinning at very high rates. We're always hoping that neutron stars may spin much faster than this, but that's for the future. And finally, one of the big problems is just why do neutron stars radiate radio waves? It's not at all clear. in detail, but this is the last illustration that I'll show you. It is because, although gravity is so strong on a neutron star, nevertheless, electromagnetic forces are extremely powerful too, because the collapse of the material of the original star brings into a tiny volume all the magnetic field that originally existed around the star and within it. It compresses it into a tiny volume. This magnifies its intensity enormously. So a spinning neutron star is really like an electrical dynamo. It generates enormous electrical voltages between the pole and the equator, and these can eject charged particles from that degenerate rigid shell in the exterior, and these particles spread around the star and form a magnetically, they form an electrical atmosphere just like our Earth's magnetosphere, and the acceleration within that magnetosphere along the magnetic axis of energetic particles can produce radio waves. Well, that is a story which would take me too long to describe now. I see that my time is up, but I hope I've given you some idea of the excitement currently in the field of astrophysics to deal with neutron stars. There are many questions unanswered, and there's a great deal to do in pulsar astrophysics. We're only just really beginning to test Einstein's theories accurately. That work will obviously continue, but there are other features too in pulsar astronomy. If we could find a very rapidly spinning pulsar, say not 600 revolutions per second, but maybe 1,000, 2,000 revolutions per second, then we would have to think that we have a different star, perhaps a star made of quarks. You could have a star made of quarks, possibly, but certainly a star made of neutrons could not spin as fast as 2,000 revolutions per second without flying to pieces. We know enough about neutrons to make that prediction. So searches for very high-speed pulsars are there in existence, and I will just say that it's a very good time to be in astrophysics now. Pulsar astronomy and astrophysics is an extremely active field, and it gives me enormous personal satisfaction to realize that, gosh, it was in 1967 that we began all this in the field at Cambridge. Thank you very much.